Now let's do an elastic collision. Let me see. What does that mean? That means we conserve both momentum always and kinetic energy. We're going to conserve them both. You would think that would help, but it doesn't. Let's see, the only way I won't even want to try to do this is let's assume mass 2 is still. So we're really just going to do the elastic collision where mass 1 comes in at V1 naught and mass 2 is just sitting there doing nothing, just waiting to be struck. Let's see, what happens? Well, let's see. We got to conserve momentum and we got to conserve energy. So let's, kinetic energy. So let's conserve momentum first. The initial momentum of this situation is m1 times v1 naught is mass 1 times v1 naught. That has to be equal to the final momentum, which is mass 1 times v1f. I didn't draw it, but you know what's going to happen. They're both going to move. So mass 1 v1f plus now mass 2 might move. It will almost certainly move. Mass 2 times v2f. So we get that equation from conserving momentum. And if you were doing a real problem, you would probably be given both masses, and this is an unknown, masses, or as unknowns, both masses and v1 naught, being say there's two unknowns, v1f and v2f. So you need to find those. So we can find them though because we have the kinetic energy also conserved. So the kinetic energy initially, this has no kinetic energy, so it's 1/2 m1 v1 naught squared is the initial, and then the final is 1/2 m1 v1f squared plus 1/2 m2 v2f squared. All right, so now in principle we're in good shape because what are these? These are two equations and two unknowns. And usually if you have the same number of equations as unknowns, you can solve for it and everything is fine, but this is messy. And the reason it's messy is because here your velocities are squared and here your velocities aren't squared. Things that are squared and added are bad usually when it comes to algebra. So what do we do when it's messy? Do we go for physical insight or do we go for a mathematical trick? Let's start with a mathematical trick. So here's a trick. And this is not something that you should intuitively know how to do. A trick is just something you have to be shown. So the trick, what we're going to do is we're going to rearrange the k equation. First we'll cancel the halves, right? The halves go away. We're going to rearrange the kinetic energy equation and bring the two mass 1 terms to the left. So we're going to end up with mass 1 times v1 naught squared minus v1f squared. Right? So there's the v1 naught term squared at say positive. We brought this one over, it became negative. And we pulled out the m1 and we've canceled the half. So there's that, and what is left is the m2 terms, v2f squared on the right. Again, I canceled out the half. Okay, so that's a trick. That helps a little bit. It doesn't help at all, actually. What we got to do is get rid of the squares. So now maybe you can see a chance to get rid of the squares is we can factor this because that's the difference of two squares. We can write that as m1 times v1 naught minus v1f times v1 naught plus v1f. No physical reason to do that. We're just doing a math trick. That equals m2 v2f squared. All right. Now let's do something similar for P, for momentum. For momentum, we also want to get all the m1 terms on the left. So we're going to say m1 times v1 naught minus v1f. Right, so that's simply this term minus that term when you bring it to the other side. And what does that equal? Let's write it over here. That equals m2 times v2f. Okay? And now I'm going to do something really weird. I'm going to divide both equations. Can you divide equations? Yeah, you can divide equations. Whatever this is, it's equal to this, and whatever this is, it's equal to that. So the ratio of these two has to be the ratio of that two. Right? It's all just numbers. Okay, so let's divide. I'll even make you a division symbol. Right? So there you go. We're going to divide those two. So if we divide these, you can see the mass m1s cancel, and this part of the factorization of the difference two squares cancels. This is where we get rid of the squared part on the left. So all that cancels, and we just have v1 naught plus v1f. And then on the right, what do we have? The masses cancel, and one of the v2f's cancel, the squared ones cancel. So all you end up with is v2f. So you get this equation that's just true for an elastic collision where you have no v2 naught. There's a special case where we have no initial motion. And that's just true. That's just true. There's that relationship between the initial and the final velocities for this case. And it's true and it's useful because now if you take that equation and you take this equation, now these two together, if I may do one of these jobs on you here, is two equations, two unknowns that are useful. So the first set of equations and unknowns wasn't too useful because the squareds lead to lots of really horrible algebra. So we guided you a way to manipulate the algebra. So now we can actually use those two to solve the problem.